Welcome to the webinar. Welcome to the webinar, ladies and gentlemen. This webinar, let's go back a slide. This webinar is Unpacking South Africa's Energy Challenges with particular reference to small modular reactors. And my name's David Nicholls, and I just start with some rules of the game. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. By default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, they are encouraged to please ask questions via the question section. A recording of the presentation will be made available on the SAIEE YouTube channel, SAIEE TV. The recording will also be made available on the SAIEE website under the events drop-down menu in the section past events and webinars. This page is updated regularly to ensure you check back as often as possible for new uploads and subscribe to our YouTube channel for more uploads. A certificate of attendance will be issued a few weeks after the webinar once we've received CPD validation number for this webinar from NECSA. Okay, with that, ladies and gentlemen, we will start.
Good morning, colleagues, and thank you for joining us this morning. My name is Naidoo. I'm part of the chapter. Let me introduce Mr. Dave Nicholls, the chairman of the Institute's Nuclear Chapter. Mr. Nicholls was appointed as chairperson of the board of the South African Nuclear Energy Corporation in January 2020 by the Minister of Mineral Resources and Energy. Mr. Nicholls internationally was the chairman of the IAEA Technical Working Group on Light Water Reactors from 2010 to 2016 and is currently the co-chair of the IAEA Technical Working Group on Nuclear Power Plant Operation. He was a member of WANO's post-Fukushima design review team from 2012 to 2018. Thank you, colleagues. Over to Dave Nicholls. Welcome, Mr. Nicholls.
Thank you, Pat. Today's webinar is looking into the electricity challenge that this country currently faces, and principally looking at how small modular reactor technology could help in that area. We've got three presentations. One I'll be giving in a second is a presentation on the challenges and looking back at what's caused the challenges and what the issues of resolving them might be, and I'm trying to do that reasonably quickly. Then Mr. Mark Mitchell will present a small reactor design that is being developed, rather interestingly, by a South African engineering team as part of a US company to provide a reactor to Canadians. So if you want international flavor, he will explain that. And you may ask why South Africa is the engineering basis of this American company. And lastly, we'll get Riedewaan Bakardien, who is the Chief Nuclear Officer of Eskom, to present the Eskom experience with the PBMR project, which essentially was the first small modular reactor proposed in recent time and could also be seen as the grandfather of the current SMR programs in the world. So with that, and we'll take questions at the end of all three presentations, because I think that's probably easier. So, pardon me. With that, I'll move on to my presentation. And as the title of the webinar said, Unpacking South Africa's National Energy Challenge, and I'll try and go through this reasonably quickly. So what I want to present in the outline is what was the historical impact of the Holt and Eskom build plans in 1998? What does the future now hold looking forward? And what alternatives for dispatchable plant does South Africa have? Then, clearly, this is a nuclear webinar, so we make no apology for being. Could a nuclear program be done quickly enough? Could it be affordable? And what's the world experience in low carbon grids? because it's important to understand that lots of models are being done about the future, but we must look at what actually has happened in the world. So with that, I'll move in. So the historical impact of the halt of Eskom build plans in 98. So I want to remember that in 1998 or late 1990s, Eskom was saying to the government, we need to build more plants starting now to meet the needs of 2007, 2008, when our projections say the power will be, our present grid will be fully utilized. It was policy then to go for the free market approach of saying, no, Eskom will not build new plants. The free market will build plants, will deregulate the market to some extent. And the aim of that was to do that. So what did that do to the situation in the country? Well, this is a very simple graph. You can see it goes from 1982 to 2019. I didn't do 2020 on here. And it plots, the orange line is in fact the actual annual peaks that Eskom achieved. And you can see if you go up to 2007, when we had the power crisis, it was a very good curve fit to a 3.4% demand growth line. And it's worth bearing in mind, this also covers periods back in 82 to 85 when there wasn't really great GDP growth. So you'd almost argue from this graph, it would appear that South Africa has a growth rate, a natural growth rate with reasonably low economic growth, but just electrification of townships, moving electric industry of about 3.4%. We are a heavy manufacturing industry country. But you can see that in 2007, it stopped growing. So the difference between where we would expect it to be in 2018 of say 54,000 megawatts versus where we actually were was 35,000. Important point to bear in mind is what this tells you is up until 2006, 2007, what you're seeing is a demand curve. What you're seeing post 2007 is actually a supply curve. Eskom ran every machine whenever it could. From 2007 onwards, Eskom was not running any machines in cold reserve in the mornings. Now, people will tell you that, but the world's changed. This graph is unfair because the whole world changed in 2008 and growth in the world stopped. Well, this is an interesting graph from the IEA, which is the OECD's body, which looks at the growth of production from a period of in this case from 1974, but you can see it is close to it. For non-OECD, that's the rich countries and non-OECD countries. And what you can see is the OECD countries did level off at around 2008. I'd argue the blip there was largely irrelevant. It just was already leveling off, and it leveled off at about a stable growth rate because they're moving the heavy industry into the OECD countries, the sort of non-OECD countries. And the OECD is the European Union, America, Canada, Australia, Japan, and so on. The non-OECD countries, yes, there was a small blip sitting in 2008, but essentially it didn't stop the growth rate. So unless one believes that South Africa is in the economic model of an OECD state, that is full employment, deindustrializing and going more to a services economy, then we have got a problem on our hands. So what impact does this have on the South African national economy? Well, this is an interesting SA Stats graph. Well, the data from SA Stats. What you can see here is the percentage of the GDP that is made from mining and manufacturing, which clearly is the bedrock of our economy. And what you can see is from the red line, which is that of manufacturing, reasonably stable at about 15.5% of the GDP was up until 2008 was actually coming from manufacturing, and then essentially a decline since then, which can be explained, if you take my thesis right, as being due to the lack of electricity in the country. And then you've got the actual mining, which, yes, it was declining up to 2008, but it got significantly worse over the period of 2006, 2008, when Eskom was in constraints of power. And you might say, well, but the economy is still growing. So let's look at that equation. This actually is emerging and developing economies. This comes from the IMF. And there's South Africa GDP per capita versus emerging developing economies. And what's interesting is that by 2021, we'll go from being substantially higher than the average developing country to be actually below the average of developing countries. And it can be argued that comes about the point in 2008 when essentially industry was told you cannot build a new plant because there is no available we can't feed the plant with electricity. This is the curve. That's the kink, little kink that occurred in the rest of the world's third developing economies. That's the same kink in South Africa, but we just didn't pick up after that. So that's a very grim picture, but it says that power suppliers are fundamental in it, and not having enough power drives the economic growth down. And then when you say, but there's been no demand, therefore there's no need for new power stations, is actually back to front. You've got to get the economy back into a state where there is excess capacity so that we can meet the needs of industry. And as power plants take longer to put in plant normally than industrial plant, then you've got to be ahead of the industrial growth. So having said that, what does the future now hold? And this is where things get really interesting. And let's just look at this a bit. Look here. So what we've got here is what used to be called the tabletop graph, but essentially is the graph looking at all the Eskom baseload power stations. Now, I'm not talking about the peaking stations. And again, if you go back into history, Eskom up until 2007 or so never ran its gas turbines. It lived entirely on these stations. And you can see all the stations: Arnott, Camden, Dover, Grootfontein, Hendrina, and so on, Coburg at the top. And Eskom's said that the life of these stations is 50 years, and I'll show you a graph in a second. And what you can now see is the age at which stations stop operating. Coburg is Eskom has said got a 60-year life. It's going through a nuclear relicensing process now, but that should be, by world standards, achievable. And you can see Medupi coming in and Kusile coming in those time periods. But what you can see clearly is that if you ignore growth for a second, from a dispatchable plant point of view, we're currently sitting with about 37,000 megawatts of plant on the system. Historically, we had the build-up as Kusile and Medupi came in, but it doesn't appear to have helped us, and I'll show you why in a second. But by 2030, we will have been decommissioning plants and we'll be back down to about 36,000 megawatts of plant. And by 2040, we'll have roughly halved the installed operating capacity on the system. And clearly, when you get much beyond that, you end up with just Kusile and Medupi being the operating stations. So something has got to fill that gap, and one could argue it through many things. But let's just look at this a different way. Let's look at this a slightly different way. And this is the performance of the Eskom stations. And I'm not going to go into great detail of this, except to say that it clearly shows that we've gone from a world-class figure of, say, 92% annual availability in 2001 down to 85%, which was essentially world average. And it's not a bad number by world averages. I would argue that 93 is too high, and staying at 85 is a good number. And then the essential precipitous decline over the last few years as we've overstressed the machines because we've run them without any ability to take them down for breakdown maintenance timeously. So let's just ask a question, well, why is that graph going down? Besides the fact that we've been running machines with no planning time because of the lack of capacity. It's just worth bearing in mind that since 2007, Eskom has not had a big unit, a coal machine or in cold reserve at all. Eskom used to run about 2,000 megawatts of cold reserve plant, so there was available plant to make up for breakdowns. From 2007 onwards, that stopped, and essentially, if the machine was able to run, it ran. So let's just look at this slightly differently. This is an age profile discussion. It's the same previous data. All we've got now is the average age of the station in 2020. So here we've got Medupi and Kusile. Kusile has got 3 machines sort of on load and 3 not there. So in the future, so that's essentially an average life of the station of 0. You've then got Medupi, which has got slightly more machines on load, about 2-year. And then you've got the older stations. Right at it, station at 48 is probably Camden. That's like Kamati. So what does this tell us? Well, standard reliability theory is very easy. It's very empirical. It ends up saying everything you buy, everything you build has a bathtub curve, so-called bathtub curve. And the first element is that the unavailability of equipment in the beginning gets better when you first have it. The manufacturing defects are worked out. And then you get a period where for the operating life of the facility, it runs very nicely, very stably, and very reliably. And then you get to a stage where the machine is basically worn out and you start getting more and more failures. And this, think of a motor car. When you have initial defects that you have when you get the car, you complain, take it back a couple of times if you're buying it, in some cases. Then it's very stable. Then you get to a certain age or mileage and it starts really getting unreliable because things start breaking down and you've got, say, 200,000 on the clock and you start thinking. And the length of this the angle of this first line coming down here is really a function of how many you built. So if it's the first you ever built, that'll be a bit of a nightmare. If you've built lots of them, it'll be very reliable when it starts up. And the point at which you start losing reliability is a function of the technology, but also the maintenance you've done in this period here. If you do no maintenance, which we know is largely the Eskom situation because of pressures, then this is a shorter line. Once you've got into this curve, it's very difficult to recover the equipment. I think we all recognize that. So what you're now seeing is, where does Eskom sit now? And it sits here with 2 stations that are brand new coming in, still being debugged. We know that from the press coverage very easily. And the rest of the stations running into old age. And even the youngest Eskom stations, Modular, is now an average of some 24, 25 years old. Which is not old, but it's getting towards the point of being old. Now, this red line I put here is purely an arbitrary one. It's a view I think is about right, but we could debate that. You certainly can run, like you can run a motor car till 1 million kilometers if you do the maintenance properly over its entire life. But you can't at 200,000 kilometers on a motor car then make up for the fact you haven't done the maintenance in the last few years. So there we are, bathtub curve, burn in, wear out, very standard thing. So if you understand that logic, then it says that we're probably in the worst possible situation now, in that we've got some stations that are brand new and unreliable, and everything else is beyond the end of its real nominal design life. Where we'll be in 2030, well, what will happen by 2030 is you've got even more stations falling off the right-hand end of the graph. Medupi-Kusile will be back to being reliable. And this is the reason you haven't seen Medupi-Kusile essentially making up the problems in the grid now, because they've been unreliable for different reasons than the older stations are unreliable. And that's probably the situation we're sitting in now. And then you may, well, how come Eskom was so incredibly good in the year 2000? Well, that's the same graph in the year 2000. It's almost the perfect graph, except that you've got to understand to do maintenance in this period to make sure you don't end up with this bottom section as long as possible. In reality, we argued Eskom at this point was too interested in being financially sound, and engineering became a secondary issue because everything was so reliable and there wasn't the maintenance being done, the deep maintenance being the long-term activities going forward. That's where we stand. Slightly depressing, I must say. So we've got to put something in place to fill this hole in the dispatchability post 2030. And realistically, what alternatives have we got? Well, here's the the graph that should scare all policymakers in South Africa. And I'm not going to get in the debate about CO2 and climate change in terms, but it's a political fact, even if it's not a, and you can argue about the science. I certainly have no opinion on that. I'm not going to make it, but it's politically a truth that you cannot, as a country in the modern world, trading country, say we don't care about CO2 emissions. What is interesting is this shows that the carbon content, the energy, the carbon intensity of the energy of electricity in countries ranges from Norway, which is absolutely brilliant because it's almost 100% hydro. Sweden is half hydro, half nuclear, and is brilliant. France is almost entirely nuclear. New Zealand is largely hydro. Brazil is hydro. Canada is hydro and nuclear. And so we go down the line till we get to the right-hand end. And on this graph, which is a graph which you can see it came from, the World Economic Forum, we're the worst. We beat Poland as worse than Poland at carbon emissions, worse than India, which tells us that any solution which is not carbon, which is good for carbon, which is not, sorry, any solution for South Africa which has any kind of carbon intensity is going to be very difficult for us to explain and probably to fund. And everyone will tell me, well, natural gas is a solution. Now, okay, we may have natural gas on the south coast, and it's clearly natural gas is dispatchable. But here comes the interesting question. Natural gas is not quite as innocent as it's made out to be. Now, this is the reference at the bottom. This is looking at the fact that because the natural gas in the atmosphere has about 80 times the impact of CO2, then the leakage of natural gas into the atmosphere from the supply chain, from the well through to the power station, actually is a very big CO2 emitter. Now, the big CO2 equivalent. What's interesting is because methane breaks down, it's methane we're talking about, methane breaks down in much faster than CO2 does. It has a much more marked effect in the shorter term than the longer term. So methane will decay in the atmosphere far faster. So it has a different impact over a 20-year average, say 100-year, but 20-year average. This is the percentage of leakage you require. So for pure heating to replace coal, if you've got 2.2% leakage of helium, of unburnt natural gas, you actually are as bad as the coal you're replacing. Electricity is better, it's 4%, and it's better because coal is less efficient than electricity than gas. A coal station is, say, 35% thermal efficiency, and a combined cycle gas turbine can be up to mid-50% efficiency. What's interesting, however, is that the plain average natural gas production losses in the US is 2.3%. I'm sure if I brought in some people, they'd argue that number's too low, but that number is a number stated by the industry. And it's also interesting that, for example, and I use an example I found of marine engines, if you buy a brand new marine diesel engine running on natural gas, you can have a design leakage of 2.5% to 4% in the actual engine, never mind the supply side. So all I'm saying here is that natural gas doesn't appear to be quite the what's the right word for it? The panacea looked at. But everyone will tell you that we can't build nuclear fast enough to meet the requirements. So what's the real history? Well, the first one is a graph which just looks at over a 10-year period, what is the fastest deployment by kilowatt hours per capita added annually for different technologies. The top section is all solar and wind, and you can see the nuclear one is the bottom. And this is not some future projection, it's actual history. So you can see Germany there, which has done major activity up to 2014, has not made anywhere near the impression that, for example, Sweden did over a 10-year period. And this is one bit of data. I'll give you a next bit of data. Is just how long it takes to build a nuclear power station. People regularly quote 10 years and all these things. This actually is the data for major programs in the world: China, France, Korea, UK, US. And what you can see is that about 5 years, 60 months, is about the long-term average for a well-run program. We could discuss easily why the US program went off the rails post 3 Mile Island about 79 and just lost control of their project. You can see the end of the French program was particularly poor. You can see the UK program, which was good back in the early days, went badly wrong at the end. So the wind down is difficult in a nuclear program, or appears to be. But you can see that the stable build programs, the Chinese, the Koreans, the French in the middle of the build program, are pretty consistently around a 5-year construction time. What does that mean in the real timeline? Well, let's look at another graph. This is, again, real background. This is the French program experience of installing nuclear. They started with the first plant going to site in 1971. That was Fessenheim Unit 1. Essentially a zero start. They got some gas-cooled reactors before that, but they imported new technology for this. And this is their program. Almost the same timeline as South Africa's program of the big 6-packs coming in terms of the years. And you can see they started in 71, and by the first machines came online by 77. And the program stopped putting new plant on the grid essentially about 88. What's interesting is they put in 50,000 megawatts of plant in that time period, and that's 15 years. And if you assume that we in South Africa were going to start a nuclear program today, which is in the present IRP, and it got to the point where by 2025 we're actually on site with bulldozers, which is what this date is, then you can see by 2030, so 2031, 32, the first machines come on. And then by 2035, we could theoretically have 20,000 megawatts of nuclear on the line. And by 2040, 42, if for the French approach, we could be at 60,000 megawatts, 50,000 megawatts. Clearly, that's not a program that anyone's projecting for South Africa, but it shows that it's very, very doable. Okay, let's move on. Well, okay, but can we afford this lot? And I'm not going to go into big economic discussions. I'll look at some stats across the world just to put this. The first one is a very simple one. This is the International Energy Agency, which is an OECD organization. This is the NEA, which is their nuclear energy, does this work every 5 years. So this is the most recent one. I presume there's one coming out this year sometime, where they ask every country in the world, what is your expected cost of construction, production of different oil technologies? And what's really interesting and why these things, this is levelized cost of energy for baseload technologies or dispatchable technologies. And what you can see is interesting because this is over different costs of capital. These are real costs of capital. So given an inflation rate of 6%, then this 3% means the interest rate's actually 9%. And similarly, if you're at a 6% inflation rate, this would mean 10% would mean 16%. I will comment that current world project financing costs for established projects, given the present situation in the world for the next 10 years, is probably down at probably between 0 and 3% real. The Egyptians just got a deal at essentially 3% in dollars, which is about 1.5% real. What you can see quite clearly is that for combined cycle gas turbines, where most of the cost is the price of gas, the assumption is that the discount rate makes little difference to the cost of the plant. If you coal plants, it makes some impact because capital. On nuclear, it makes a much wider impact. That essentially the median of nuclear at 3% cost of capital real is but it's below $60 a megawatt hour, and it goes to 120 at 10%. Which is why you'll often get people saying we must use realistic, quote, realistic costs of capital. They will give you figures like the current South African IRP is based on 8.2%, which is between these two numbers here. Although the financing offers for any nuclear deal, including the Nuclear One deal of 2007, was actually below this number here. But that's a theoretical calculation, but it's based on every country in the world being asked what is their number, and in the US, it's a worthwhile report to look at. If you then ask the South African situation, where do we stand? And this is a graph I pulled off the annual report, 30th of January last year. What's interesting to point out is that this is the tariff in the world, and I'm going to forget Argentina because their economies collapsed, so their peso is worth almost nothing, which is why it's down so low there. But if you look at this list here, which Eskom published, you go from Germany at 33 cents US down to South Africa 9 cents and Eskom at 7 cents. The difference being because of the domestic customer rates between Eskom and the Munichs. What you can see, of course, interesting enough, is that if you look at the countries like Argentina, China, India have large nuclear build programs. Indonesia is trying to get nuclear built. Canada's got nuclear and hydro. It's rebuilding its nuclear stations. South Korea is heavily nuclear. Brazil's hydro and it's building another nuclear plant. The US is very cheap gas and is also building a nuclear plant. But Turkey is building 4 nuclear units today. Poland's just announced they're going to go nuclear. Finland's building nuclear. Colombia, I can't comment on. I think it's hydro, and so on. France is nuclear. So you can see that this end is full of people who think nuclear is good. This end is Germany, Belgium, Italy, Portugal, Spain, Austria, which think nuclear is fundamentally not good. I'm not sure who's right and who's wrong. You can work out yourself. There's another graph just of the cost of energy, a different selection. Again, 2017, and again, South Africa's down here with India and China and Brazil, Czech Republic, which is planning to build another nuclear station. Canada, Poland, Finland, Slovakia is building a nuclear station, and so on up there. There's France. The Netherlands actually is quite cheap because it's got wind and it's linked heavily into the Nordic grid, which is cost-effective power. People will say, but surely we know the lowest cost is renewables. That's what the South African government, the IRP, has said. This is the CSR. I think it's the 2016 result, but it's the same thing. This is the price path in the IRP. This is the correction because Eskom's tariff is currently too low. So in 2017, they were saying it must go from 80 cents to R1.10 just to make Eskom viable. Again, if you don't, but what's interesting is that it then goes on growing. This is therefore the viable historical number based upon using classical power plant design and technology. It steadily grows and it kinks and grows up further from about 2037, which is when every coal station's disappeared. So this is the free market, no Eskom, no classical power station discussion, and this is the transition from Eskom at the correct tariff through to the end of Eskom, because by then you've got Majuba, Kendall, and you've got Medupi and Kasili running. But so that's that. So interesting discussion. So but I've said low carbon and cost are the two issues that must drive us going forward, and I've said the lack of capacity, lack of dispatchable capacity is what's currently driving us. This is a quick graph. This is one of studied on an hourly study of the European grids in the summer of 2017 by an excellent. If you go to electricitymap.org, you'll find a live emissions chart. What is quite interesting, just to show you, is that everyone says if you're going low carbon, the example to follow is the Germans, because they're the ones who lead the way. Now we've seen the highest tariff, but the highest tariff therefore should be reflecting into, given their policy, should be reflecting into lowest CO2, and this is the European states. And this is the world, and you can see on the left-hand side, Norway, Sweden, France, Czech Republic, that's Switzerland, which is interesting because Switzerland is 40% nuclear and the balance is hydro. Finland is nuclear and hydro. Belgium is a lot of nuclear plant is planning to decommission them. Austria's largely hydro, and you go along this line till you get to the really expensive, successful transition to a clean economy approach, which doesn't seem to be working desperately well. Here, by the way, it's of interest to go with it, is actually what was the energy produced in Europe, and you can see the graph. But what's interesting is the biggest single supplier of energy in Europe in summer of 2017 was nuclear. Solar is over here. That's hitting zero on a regular basis and occasionally being up to 20% of the grid system. There's wind. It never gets quite as low as solar, but it gets down there, and so on. So it would seem to me that the solution might be obvious to those who look at the numbers. And this is my last slide. So I've been going a bit longer than I probably should have been. And let's look at the world's low carbon grids, actual large low carbon grids. And the size of these circles is a function of the energy they generate. And what you can see is, let's go from the top down. France, 75% nuclear, hydro for that section there, and then they've got fossil fuel for a bit, and wind and thing, but they are a nuclear with hydro coming from the hydro plants in the Alps. Quebec, virtually all hydro with a bit of wind, but you can see the wind is probably not commercially, it's probably a policy issue. Ontario is nuclear, hydro, and again a bit of fossil. Sweden is nuclear and half nuclear, essentially half nuclear and half hydro. Used to be, it's now got more fossil because the nuclear has been shut down by policy decisions, not by economics. Norway is entirely hydro. Anything in Norway that's not hydro is almost either a complete peaking station or is a policy issue. I mean, the Norwegians are now building wind turbines to displace hydro. I don't understand the logic of that. British Columbia, which is again largely hydro with a bit of thing. Paraguay is beautiful; it's entirely hydro. Switzerland, as I mentioned earlier, is largely hydro at 40% nuclear. So with that is my last slide. what I'm trying to say is that South Africa, the energy problem we have in this country is a function of policy going back. The solutions on the table is probably not the correct one. It has not worked anywhere else in the world. There's nowhere in the world that can put up a renewable solution which gives you low carbon and gives you low prices. Hasn't existed in the world as a whole. What has given the world is a combination of hydro and, where not available, nuclear. And we have no hydro. We know that. We're a pretty dry country. So on that basis, I'm going to now pass across, having given a problem statement as the beginning of this thing, and rather a long one, I intend now to pass across to Mark Mitchell, who is the who will give the next talk about the other end of the scale in size. Nuclear is always seen as massive and large, so I'll introduce you to Mark Mitchell. He's a nuclear specialist. He's responsible for the development and deployment of the USNC micro-modular reactor. He's a trained mechanical engineer who focused on power generation, and the majority of his career has been focused in nuclear power. He graduated from the University of Pretoria in South Africa, started out his career in defense and aerospace before he joined the PBMR project. His major contributions were establishing the fuel handling and structural analysis capability, leading the graphite core assembly team, and later taking responsibility for the design of the reactor systems. So with that, I will pass you across to Mark. So here is Mark for you.
Hello, everyone. Let me just switch over. Right, thank you very much. Dave, thanks for the introduction. So I will be giving a short talk about micronuclear and the work we're doing there. And I guess the idea is to share a flavor of what's in the pipeline in terms of future developments of nuclear. Maybe before I dive in, just a quick check. Can we see the slides?
Yes, I can see the slides.
Perfect. Great. Thank you. So, I'll use our project and the work we're doing as an example, and I'll invite questions about the broader scheme, and also if there's anything that in terms of interpreting what we're doing and how this will probably affect future generation. First, just a little bit about USNC. As Dave mentioned, we're a US-based company. Our headquarters are in Seattle, Washington. We're actually pretty much spread out over the world. We're in 6 countries. We have about a team of about 50 people in-house, and probably extending to about 100 or a little more than 100 people working on our first project. Founded in 2011, really looking at our special fuel. And so we've got 3 areas of technology we work in. First is our fully ceramic microencapsulated fuel, which is a extremely robust and accident-tolerant nuclear fuel. And on that technology, which is proprietary to us, and we've been developing it in the labs before 2011, and of course for the last 9 years independently with private funding. Developed on that fuel is the micro-modular reactor technology. And this is a tiny reactor designed specifically initially for off-grid applications. It generates about 5 megawatts of electric power. And I'll give you a bit of an overview of that and some of the logic around that and how it fits in. Just for fun, I'll also mention that we also have another division which works on space nuclear, so both space nuclear power and nuclear propulsion from NASA, which is always a lot of fun to speak about. Unfortunately, I won't be touching on that in this discussion. Our micro-modular reactor program is essentially in a race to provide power energy to remote mines and communities, first in northern Canada. Really, the idea is to do nuclear not like nuclear is done today, but a lot more like renewables. I think when I talk about the team has a South African component, and I'd point out that there's some very interesting things about South Africans and their value in this industry. Firstly, the large number of advanced and micro nuclear and SMRs in development in the world today probably owes a lot to South Africa's pebble bed program in the late 90s through 2010. And this is this was an incubator, and it also showed people a new way of doing nuclear, that small reactors might actually be a way of being economical, addressing a lot of the problems. And I think one of the things I learned out of that is that even small modular reactors are too big, and that's why I've ended up working in micro reactors. But let me park that. I think the second thing is that around the time PBMR shut down, 2010, we picked up on our refit or REAP program, and that really meant that a lot of the people leaving nuclear and looking for something else to do in power ended up working in renewables. And that was an extremely valuable experience, and I think a lot of the South African guys on our team have exactly that history, and have actually learned a lot about new business models and new ways to deploy technology that really will make a difference in terms of changing how nuclear approaches this. And yeah, I think we're looking at accessing a probably in terms of power and energy, a modest market at first, but a pretty big market, which is really worth the effort. So the real question is why? We have ways to decarbonize electricity. We have, we can generate power today. It's not a small lift bringing a new technology to market. Why do it? And I think there are two thoughts that I would share there. The first is we don't believe in doing something if we're not addressing a real and immediate need. And we also want to see what we do to address the real immediate need not to be a dead end, but to have a potential for growth and to make a bigger impact. And I realized while discussing the world of nuclear with policymakers is that a lot of the ideas that we have are not yet valid policy options, in that they're not real. You can't buy them off the shelf. And I think it's an absolutely key point in our development life cycle where we are with small nuclear, is getting over that hurdle, going from paper and ideas and PowerPoint, more likely PowerPoint and Zoom calls right now, to actual implementable, purchasable products. So firstly, we talked about an immediate need. There is an immediate need. Just for interest, Canada does a lot of mining. You'll find, the contribution of mining to the Canadian economy looks a lot like South Africa. In fact, probably looks more like South Africa 10 years ago than today, as Dave pointed out. And this is a sector that is both growing and under a lot of pressure for environmental responsibility and other driving factors. So we're looking at remote mines, really, and communities that grow around the mines, or communities perhaps near mines, or just communities. We're looking at providing them with power. Today, these communities are powered generally by diesel. And this is not just diesel, this is diesel with an incredibly challenging logistics and supply process. So for instance, one of the mines that we studied, if I recall the numbers just right, was using 55 million liters of diesel a year. And that was shipped up over winter roads or ice roads during about 4 weeks when it was cold enough and the ice was stable. So that's great for Discovery Channel TV, but I think there are some questions about the sustainability and the environmental impact, and just, with climate change and warming, we're seeing that period is actually shorter, and this is not This is measured. This is not speculation. So anything running on ice roads sees risk. And in fact, there was a example of a mine in the Northwest Territory a couple of years ago where the ice roads failed. And if I recall the right number, I think it was 1,100, so 1,100 C-130 loads of diesel were flown up and used to keep the mine operating. And that was probably not at full efficiency. So there's an immediate need. And we see this as the way to launch this product. It's very hard to serve any other way, but diesel, we think that this is a good place to demonstrate micronuclear. We also know that this is a place where micronuclear is cost competitive, so it solves a problem and it makes economic sense right now. We see that as our first act. And I'll point out that there are many places in the world that are similar to this. So when we're embedded and operating in Canada, we do see extending this model to other parts of the world. But that's not where it stops. Dave mentioned the political reality of decarbonization and controlling emissions. I guess I'm not, if you ask me my opinion there, I think it's a physical reality as well. I think it's something we have to come to grips with. I think we can't grow indefinitely without changing where we get our power from. And this is the IEA energy technology perspective. And the IEA embraces this and has a target for sort of the 2-degree world, I think they call it. And what you see here is a projection, if all of the technologies that they're targeting are implemented, of the effective reduction in gigatons of carbon dioxide over the period, 2015 to 2050, sorry. There's already a significant contribution of nuclear. But I think what's important to note here is that if you look at the dark blue section of the chart, in 2050, about a third of the total carbon emission, even under the scenario where everything works out, remains industrial. And in fact, the industrial contribution doesn't change that much. So essentially, we're getting really good at decarbonizing electricity generation, but we haven't really got a good plan to decarbonize industrial processes. Now, effectively, if you read the report, the only real plan there at the moment is carbon capture, sequestration, or use. And that's not really on track to the extent that the IEA would have liked it. You can follow, there's a link in the presentation. You're welcome to follow that, please. Take a look and see what they're saying. And I think that high temperature gas cooled reactors, the technology that we work in, and especially ones at our scale, which can produce 15 or 30 megawatts of heat, are absolutely perfectly suited to contributing to that decarbonization. And in fact, they're also really well suited to making economic green hydrogen, which is probably the next big thing in terms of power generation. So, we see a great, exciting world, and we don't see it only being in terms of making electricity. And that's really why. So a little bit about our technology. I'm just going to put this slide up here and draw your attention to the QR code. So if you want to take a look at this and play with it, we have an app which creates an augmented reality version of the plant, which you can sort of click around and examine, and can give you a bit of a better feeling for what we're talking about. So the link in the QR code will take you to the tabletop MMR app. This is a typical plant for remote power. This is 2 reactors. It will generate about 10 megawatts of electricity. The remote power market is interesting. That what we know is that we cover about 90% of the market if we can generate between 5 and 50 megawatts electricity, and that would be 1 through 10 modules. What you'll also see here that's interesting is that this is set up for high availability. We still have some backup diesel generators. Those are absolutely not, like in the case of a current nuclear plant in any way associated with the nuclear plant, they really are so that if we take a nuclear unit offline for maintenance, we can keep providing high availability power to our clients. Some other interesting features, these reactors, they're designed for a core lifetime of 20 years. They're not refueled, they're deployed, operated, and then broken down. You could extend the lifetime of the plant if you wanted. That's absolutely simple to do. The reactor technology I'll talk about a bit later, but something that we do that's very interesting is that we use molten salt as a thermal energy storage, and we actually buffer we have a buffer between the reactors and the off-taker. And the reason for that really was driven by providing power or energy, because it needn't just be power, to an integrated energy system connected to a secure and reliable microgrid. So this is nuclear for microgrids. It's not just nuclear. It's not just nuclear that plays well with renewables. It's actually designed to work with microgrids and to integrate with any generator that's on the microgrid already, or if we were to install wind turbines or something as well, we could do that. That is the level of flexibility we've achieved, and all of that is based off a rigidly standardized nuclear plant. So the idea is that this plant is licensed, and using the energy storage, we can move the nuclear plant effectively to work against the microgrid. Now that's really interesting, because what this configuration allows us to do, for instance, is operate with the same good nuclear economics, even at mid-merit or potentially peaking operation. So that's really exciting. We're going to claim it's strategy, but the reality is that when you're working on a microgrid, your generators have to be able to follow the load. There's just no other way to do it. And so effectively, we've looked at optimizing the plant for that. We can combine with any new technologies, energy storage. We integrate with all to optimize the solution we would deliver to the client. So that's an overall picture of a plant. Our key technology that this plant is based on is fully ceramic microencapsulated fuel. Essentially, this is probably going to be the toughest nuclear fuel you can buy. And really the idea that we have, and the name of our company, UltraSafe, reflects this as a challenge both to ourselves and the industry, is that nuclear safety needs to be ensured from the inside out. And when we talk about nuclear safety, really the key thing that differentiates a nuclear plant from any other generator is the creation of radioisotopes, fission products, which can have harmful health consequences if released to the environment or the public. And the idea behind this fuel, which is based on probably 50-year-old technology of TRISO fuel, and embedding it not just in a convenient matrix, a graphite matrix, but actually embedding it in silicon carbide, which is an extremely robust and resilient material. In fact, it's one of the key protective elements of TRISO, is that you can set up fuel that, when used in a reactor like ours, cannot be compromised. So it's not eliminated by argument, it's practically eliminated. This is absolutely eliminated. There's literally not enough energy in the system to damage the fuel. And that means that the radioactive fission products stay in, and that gives you a very different approach to safety to the generation of reactors that operates today. The reactor is very simple. If you've ever looked at gas-cooled reactors, this will almost look like a picture from a textbook. But this is our core system. This is our nuclear system, the nuclear heat supply system, we call it. I apologize, we're engineers, so things are called what they are. But the simplicity here is almost hard to explain. I think the easiest way I found to explain this is say that the entire NHSS has 10 moving parts. And that is probably about as simple as you can get it. it essentially has very simple characteristics from the perspective of control. There's really very little to it that is new, and really our decision choices here were made about getting to the market quicker, getting the plants operating, rather than trying to design the most advanced and specialized technology. A question we get a lot is, is this really a first of a kind reactor? Is it new? What I'd say is that the second commercial reactor built, 58 if I recall, was a gas-cooled reactor. So gas-cooled reactors are nothing new. High temperature gas-cooled reactors, also about 60 years old. In fact, today in the world, there are 2 reactors using the same technology and the same class that are operating. And in fact, between those reactors, they completely envelope the design parameters for this reactor. So I think it's a different way of doing something that exists. I think there's a lot of room to improve things, but fundamentally, this is not a new technology. And I think the reason why we chose that again is to simplify our path to applications. So I'm always in the awkward position of a tech company, a new nuclear guy, explaining there's nothing new. But that's also not entirely true. I think we've restricted our innovation to areas that matter. The first is the fuel, the fully ceramic microencapsulated fuel, because that just brings such good improvements in safety and operations that it's worth it. The second, of course, as I mentioned, is using the molten salt intermediate heat transport loop. And I'd point out that this was an idea we even had back at PBMR. This is not an absolutely new idea. The problem is it was a science project then. But in the 10 years between that, we have more than 3 gigawatts of, in fact, I should update that because the 3 gigawatt number I use is a 2016 number, of concentrating solar power deployed. And a lot of it is now using molten salt, either for heat transfer or for energy storage. And so we've got really, really good experience there. And that was a technology that wasn't available 10 years ago. And it's maybe not as exciting as self-driving cars or drones, but it's probably as revolutionary. Another thing that our reactor forces us to look at is modularization. And I think that this provides, microreactors, the MMR, provides an approach to modularization, which is quite radical. It's not building modules the size of, well, buildings on the site and moving them into place to try and accelerate construction. It's modular on all levels, in fact. It starts off with being very applied for distributed generation, very applicable. It allows you to use a lot of new applications, smaller quantum investment, reduced losses. It goes down to standardized units where you have plant configurations that are repeating. You get into mass production, not just repeatability on paper, but actually out of the same factory. And then you get to modular construction, and this is absolutely necessitated by applications because our goal is to be able to deploy this over an ice road if we have to, or winter road. And that means that these modules have to be small enough to fit on the back of a truck and light enough so that they don't fall through the ice. And so that's the idea. And these modules are fully interchangeable, fabricated and tested off-site. And when we take them to site, we install them, we don't construct. So eliminating construction is another area where we can make a big difference to the economics of nuclear in terms of the risk profile in construction. We are unusual. We sort of understand that with the somewhere near 160 advanced reactor concepts being touted, of which about 60 of those are SMR, that there's a lot going on in the talking space. And we don't really want to participate in that. We want to make this real. You know, an idea is only worth so much. And so that's why we're focusing very much our effort on the deployment of our first reactor. We are, I would say probably, but actually we are the most advanced commercial Gen 4 reactor project in the world. We have, this is a summary, and I've just given some external references for those who are interested. But really, we are developing a project to deploy a reactor at Chalk River, and we're in the process of licensing that already. We've completed our vendor design review. We have been selected to receive a site for the demonstration, and we're in the process of negotiating that. We have a licensing process underway where we're currently following the Canadian licensing process, and the first step in that is to secure an environmental assessment and a license to prepare site. That's been underway for, I think, 18 months now. And we have a partnership with Ontario Power Generation. The partnership's called Global First Power, and this will build, own, and operate the plant. So that's really good progress, and we expect the plant to be built on one of the following sites. Excuse me, I've switched to the GFP background just so we can see where this is sourced from. But essentially, we've got a preliminary selection of 3 sites at Chalk River we're investigating. We're in the process of doing the EIA. I'm sure that the preferred site will be announced quite soon. And this puts us on this timeline here, which essentially will have the first of kind reactor, the Chalk River demonstration, operating in line with CNL's target date to have a reactor operating on the site again by 2026. Naturally, we think we'll move faster than that, but we are a little circumspect about our actual dates. There's still a lot of risk. There are a lot of things we're going to have to overcome. There's a lot of work we have to do with public engagement and Indigenous engagement of the Indigenous people, and just making sure that everything works and works on time. So really what we think this will enable us to do, shifting gears here, is to set up probably the first vertically integrated nuclear IPP. That's structured like renewables, effectively. That allows us to use mass production to learn, recover initial investments, and to build these simpler and cheaper and quicker than we've ever witnessed in the industry before. And also to reduce risk, and probably the biggest factor in that is by simplifying and accelerating licensing and construction. So I'll leave you with these thoughts because I'm convinced that small nuclear is coming, and I think that micronuclear is probably going to be a game changer in terms of small nuclear as well. I think that what people call SMRs today are just too big. But this MMR vision of the future really changes potentially the way we deploy nuclear by a factor of 10, right? So we start to look at development costs that are 80 million, not the 800 odd million that NuScale published. You're looking at shorter construction times, assembling the plant in 6 months, not 60 months, 5 years. A lot less work up front in project development, more like a renewables project, 10 million, not a billion. I think that if you ask anyone else on the call, the approximate investment it takes to develop a nuclear project to the point where you start construction, 1 billion is a good industry benchmark figure for a gigawatt class plant. Less money to build the first unit. We're looking at investments in the 100 million, not the $1 billion range. And higher numbers of unit sales, 10 unit sales, hundreds of unit sales, not a single unit, or somewhere between 1 and 10. And I think these are the kind of possibilities that the work we're doing should unlock. And yeah, I think we're looking forward to seeing what the future holds. Dave, thank you. I think that's what I have to say. Can I hand over to you?
Thank you, Mark. Excellent presentation, and I find it fascinating that we're starting to get back to an era which reminds me of the 1950s and 60s, where people were talking about nuclear plants the size and weight of a diesel generator. It's interesting to bear in mind that in the very early days, the US Army was looking at had done designs of plants that were, I suspect, in many ways very close to what you're talking about, but literally planning to build plants that were competitive at the 5-6 megawatt diesel generator size. So interesting discussion. I'm now going to move on to the last presentation. We're going quite slowly. It's been a bit longer than planned, but I think these are excellent. Last presentation was fascinating. South Africa did lead, at one point led the world absolutely in small modular reactors. And I will prejudge Riedewaan because he's about to come on and comment that when I first started PBMR in the 1990s, I don't know, 1990s, I remember going to the IAEA, UN body, and talking about a 100 megawatt nuclear reactor, not the 5 megawatt that Mark was talking about, and being told that it wasn't possible to have a 100 megawatt commercial nuclear reactor. That they had decided that anything between 1200 megawatts up was large, anything between 900 and 1200 was a medium-sized reactor, and a small nuclear reactor was 600 to 900. And there was no such thing as a commercial reactor below 600 megawatts. And I think it's fascinating that in the time since then, maybe it's 25 years, we've got to a stage where it is now almost accepted wisdom that very large nuclear reactors, the 2000 megawatt machines being talked of a few years ago, are not really viable. And I would like to be proud of South Africa in actually stating that Eskom led the way in trying to discuss how you actually commercialize a small modular, what wasn't called, but essentially a small modular reactor. And I would like to be part of the team that I think moved the world scales. And Riedewaan was also part of that team when he was in that thing. So I'm actually to Riedewaan Bakardien. Riedewaan is Eskom's chief nuclear officer, responsible for Eskom's nuclear activities, notably the Koeberg nuclear power station, which has been the only nuclear station in Africa since commercial operations started in '84. He holds a Bachelor of Science in Mechanical Engineering, as well as a postgraduate diploma. He has 25 years of experience in the nuclear power generation field, having worked in maintenance, outage management, engineering, nuclear new build, and nuclear power management. And I'm now going to pass across to Riedewaan and ask him to go to a presentation on the background of what Eskom's experience with PBMR was over the years. So Riedewaan, over to you.
Thank you, Dave. Would it be possible to take control?
Yes, I've given you control.
I see I've got it. Okay, great, thank you.
I'll now go quiet.
All right, so I will take it from here. Thank you, Dave. And yeah, it's really great to hear the work that USNC are doing, and an exciting future for the nuclear industry. And a lot of it, though, we've got to look back at what came before, and that is, I believe, set us up for being able to move into the future of nuclear around the world. I believe there's more than 50 reactors being of the SMR type being developed, put on paper around the world. So there's a lot of interest, and yeah, Mark, good luck for USNC. And we look forward to you guys being part of that exciting future. So I'm going to talk a little bit to the South African experience of nuclear and Eskom's experience of nuclear as relates to the high temperature reactor project PBMR that was that we had been busy with in the 90s and noughties. Excuse me. Right, so if I can just start off with going to some of the history thereof. And this comes from the South African experience on the small modular reactor, on the high temperature reactor, was based on the founding technology developed in Germany between 1965 and 89. And that was related to the AVR in Germany. It was a small 15 megawatt reactor, and then the THTR, which was a follow-up to that. There were some other reactors, and I see Mark also mentioned the Chinese 10 megawatt HTR, which they've used now as the basis for the reactor that's being built, which is a slightly larger reactor that's currently under construction, a 200 megawatt electrical output reactor or plant. And the development in PBMR started in South Africa in 1993. Dave Nicholls, the person we just heard, was quite influential in that development and the initial exploring of the future for PBMR. Importantly, South Africa and Eskom then acquired the license of the HDR from Germany. In 1999, we created a client office in 2000 to receive the plant, and we were the work was proceeding at that stage to move towards demonstrating and building the first plant. And a detailed feasibility study was done in 2000 with Eskom, the IDC, BNFL, British Nuclear Fuels, now Westinghouse, and PECO, which is now Exelon, a utility in the US that still runs nuclear power plants, as part of a cooperation agreement to actually fund the development activities. And that feasibility study concluded in 2002 that PBMR should be demonstrated. So a lot of work that was happening at that stage. And in 2003, Eskom then effectively handed PBMR over as a company with its various funding that was obtained through the various sources. And from 2006 onwards, government then was the sole provider of PBMR. Eskom, though, remained as the client for the project, so wanting to demonstrate and receive the technology as the owner and operator and responsible for licensing of the plant. Unfortunately, in 2008, and this is now a well-known history, the government of South Africa stopped funding the PBMR project. That was also at the same time as the financial crisis, and obviously there was a reflection done on what activities to proceed with. But at that stage, the work had advanced quite far. With the development of the design, starting manufacturing activities, the licensing, getting the approval for from an environmental perspective to confirm the technology was fine. The intent was to construct the first unit, the demonstration plant at the Koeberg power station in Cape Town. And unfortunately, due to the fact that PBMR could not secure any additional funding, the Cabinet then decided in 2010 to put the project under care and maintenance, which is where it's been since. And the PBMR technology was then reincorporated back into Eskom in 2012, when we've been managing the project under care and maintenance. And there's quite a lot of infrastructure, there's facilities, there's IP, codes of design and analysis that was put together as part of that project. So huge IP, which is currently still being maintained in the same form as it was in 2010. And that's where it remains to today. So just some of the milestones on the project and what actually happened. Eskom issued PBMR with a user requirement specification for the plant in 2000. And the nuclear regulator, the NNR, issued a positive view on the licensability of PBMR in 2003. That was a major milestone, confirming that this could be developed and built in South Africa and would meet all of the regulatory requirements of the NNR. In 2003, DEET, the Department of Environmental Affairs, issued a positive record of decision on the environmental impact assessment, based on the fact that it met all of the requirements. Unfortunately, legal challenges then took this back, and it was actually the record of decision was thereafter set aside due to procedural flaws in terms of how the the EIA application had been done. In 2004 also, the project then moved to DPE in government, public enterprises, as a national strategic project to demonstrate the technology. Because of the record of decision being overturned on the EIA, it was restarted in 2005. A decision was made to restart because of some changes to the PBMR design, which I'll talk about a little bit later. Eskom then issued a letter of intent to procure up to 4,000 megawatts of the plant. At that stage, there was quite a lot of work happening. In 2006, the NNR issued a suspension of manufacturing activities. Interestingly, at that stage, the reactor for the plant the manufacturing had already started, and the construction of a number of other activities for the reactor and other parts of the plant. That was eventually lifted then in 2008 to restart the manufacture. And in 2009, the final environmental impact report was issued. However, it was quite late into and as I'd mentioned, in 2008, government decided to withdraw funding. So the EIR was withdrawn in 2010 due to the project status. So just Eskom's involvement on the project. In 1993 to 97, there was a small team performing the pre-feasibility work to confirm that what technology we would want to develop, and what would the business case to look at the initial business case thereof. PBMR was established as a company under Eskom Enterprises. That's a division in Eskom, and later under PBMR, the PBMR company itself, Pty Limited, was established and run under DPE. And in the years from 1999 to 2003, Eskom was an active investor and the project developer. And for 10 years, we also ran the client office, with the responsibility to host and operate the power station. So we'd set up the training requirements, the initial requirements for training up our operators, the requirements for running the plant, and to then also take the lead for the environmental assessment and the licensing of the plant with the nuclear regulator, and the assessment of PBMR to ensure compliance with all of our requirements. Also important, preparing the site staff and services required to operate a nuclear facility. So the initial staffing for the operation of the plant had actually been, we had acquired that staffing in the mid 2000s to prepare for the operation. The experience in terms of licensing, with the nuclear licensing requirements being developed as the project evolved, licensing of this was not a simple task. So the rules were being written as for a high temperature reactor design as the design was being matured, and the strategy to define the licensing matters between the vendor, which was PBMR, and Eskom, as well as the regulator. We decided to list all of the higher risk issues and define those as the 25 licensing issues to ensure those were managed. And the good progress was actually made on resolving virtually all of those licensing issues. The learning from the interaction with the regulator in 2006 was painful, because it did set the project back when the manufacturing was suspended for about a year to implement robust safety culture requirements as the NNR had specified. Also improving manufacturing specifications, oversight and control measures. But in retrospect now, that also assisted PBMR in implementing processes to become a competent nuclear vendor. Those same rules will be applicable to any other nuclear projects in South Africa, including for activities now at Koeberg, meeting those what was initially elevated requirements for the PBMR. Much more stringent management of the control of manufacturing and design activities. And then by the time the project was stopped, but virtually all the licensing issues had been resolved, and so we were pretty much ready to go. But there were unfortunately design changes that had occurred during the years, and I'll talk to that a little bit in the next few slides, which did complicate licensing. So it meant having to reopen issues due to changes in design and size of the reactor. And it's important that for any new reactor being designed, that regulatory certainty and its impact on nuclear should not be underestimated. It's important that there is regulatory guidance upfront to a high level to ensure that when you're doing your design, you know what you need to what the requirements are that need to be met in that particular country to ensure that it can be licensed. And designing a plant in parallel to licensing is very complex, and that was one of the challenges that PBMR managed to navigate through. And at the end of the project, by the time the project was terminated, the design was pretty much matured, with most of the licensing issues having been resolved. In terms of the technical challenges and experiences, PBMR was an attractive prospect to Eskom due to excellent reactor safety driven by low energy density. We speak about generation 4. This was the generation 4, the reactor design at the time, and hence the interest from some international parties as well as Eskom and the South African government. The high plant efficiency, over 40%. Currently, the nuclear reactors, the larger reactors, we're looking at just over 30% plant efficiency. Also, the low postulated cost of generation, equivalent to or less than the current reactor or nuclear options out there. Obviously, the short construction time, not as short as what the USNC offering is, and as Mark described, but still significantly reduced from the large reactor designs, and low radiological impact, and basically no requirement for any emergency zone. So it could basically be situated in the middle of very busy areas, and without any concern. No event could happen at the plant that would endanger the people around the plant. A process, so just in terms of the design methodology that was used, and it really was quite revolutionary or at the time. And a process and information flow model, the engineering enterprise architecture for the whole nuclear development process was developed and integrated for all stages of the project, right up to construction. And a world-class integrated management system for quality assurance, managing all of the requirements from whether it's Eskom or the regulatory requirements. The analysis management system, so all of the analysis that needed to be done, the software management system, product data management system, the nuclear engineering analysis, all of that was compliant with the nuclear quality assurance requirements of NQA1, which is the international nuclear quality standard. I think if one then goes on, the designs, that infrastructure that was set up was quite important as the design was developing, and it evolved from initially a 268 megawatt thermal reactor design to progressively larger, up to 400 megawatts design. So that's the thermal output of the reactor. You'd be looking at around about 160, 170 megawatts electrical, if you're using a efficiency of over 40%. And there were major philosophical changes over the period of the design, ranging from initially a vertical floating turbine and turbo machinery to a more standard turbine and generator design, based on what was available in the industry at that time. The intent was to not to use equipment that was not available. So there were arrangements and contracts already set up with equipment manufacturers for turbine and generators, as well as reactor manufacturing to provide the equipment. And it was available or could be designed and developed at the facilities and factories around the world. And it must be said that we had links to many countries internationally who were formed part of the supply chain for the project. Also, the reactor design was changed to an annular design, and eventually there was discussion of an indirect cycle design being proposed. That was related to a proposal for the US next generation nuclear plants that were under discussion at the time. There were various material risks, and particularly the turbine material risks identified in the late 90s. So development of new materials by competent vendors were required, and that would take years to prove and then demonstrate the components prior to use in the reactor and in the plant. And in some cases that was still being resolved when the project was closed. And two principal processes were used to perform the engineering oversight. So design assessment to basically confirm that the design inputs and outputs could be met, and the technical surveillance to confirm the acceptability of the engineering and analysis processes used in arriving at design solutions. So that's to build certainty that your assumptions can be met and your calculations are accurate. Eskom followed a risk-based approach to select the areas to be evaluated and the depth of evaluation being commensurate with the risk of the topic. So some of the activities that Eskom Client Office was involved with at the time and that was progressing was the codes and standards for the design and manufacture of all of the parts of the plant, specifically obviously the reactor, the main piping and turbines, and the recuperator. There were issues and concerns raised around the leak before break of the main piping, which was an important design issue, and to also part of the safety assessment and the requirements of meeting the requirements of the nuclear regulator. The reactor neutronic codes were developed and quite well matured. Fuel design and qualification, core ceramic structures qualification, turbine materials, and a number of other issues. And safe to be said that a lot of this had actually advanced to quite it went to quite an advanced level. Fuel manufacturing had been progressed quite far. The testing has been conducted in subsequent to the project actually being shut down, which has proven that the fuel manufacturing done in South Africa at NECSA was produced fuel that was of a very high standard and would meet the requirements for the reactor. So that is the basis, I believe, on which a lot of confidence can be created. We've seen even, and with the discussion of Mark, the fuel design is at the heart of the safety of the plant. The thinking being that irrespective of what happens on the plant, it is safe to shut down and it's effectively walk away safe. The larger the reactor becomes, the less guaranteed that is, however. So smaller reactors, it is much easier to get that assurance, and the calculations are much easier to do. The testing that needs to be done to prove that is largely already done, and the operating experience from the German OE can be used for a lot of that. I think the challenges often came up with pushing the design envelope to beyond proven capability, where it became a challenge to be able to license those items without significant R&D being required. So in conclusion, the evolution of the legislation worldwide has given rise to what we now call generation 1, 2, 3, and 4 type reactors. most popular design, and Koeberg Power Station being one of them, the pressurized water reactor can at best achieve, and reactors of a similar design can at best achieve generation 3 status. The high temperature gas reactors, such as the pebble bed, can comfortably meet the generation 4 requirements. And that was really the bottom line why the HTGR was and still is a highly attractive option for the future. PBMR, because of its reactor safety benefits, is still an excellent option for the future. What it does though take is you've got to get through the demonstration of your first reactors, the licensing thereof, and that is where the world today sits, with nearly all of the reactors that's currently on the table, to be able to demonstrate and license those reactors and then go and construct them. And we're looking at about 5-6 years into the future to get that then ready to run those plants and to commercialize the technology. The lessons that from the PBMR project has really been good for Eskom in terms of our understanding of the requirements for nuclear new build, but even for the operation of Koeberg Power Station and the improvements in the quality assurance, the safety measures, the analysis has helped in that space. And from a project management perspective, in retrospect now, I believe it had a low probability of succeeding, as the funding was never fully secured for completion. So with any new reactor that gets put on the table today, it's important that the full life cycle up to completion of construction, commercialization, and even for the operational phase to decommissioning, it is fully understood and then funded as part of the project. Chairman, Dave, that's it from my side. So I'm going to hand back to you then. Thank you.
Rule 1, unmute yourself at some point. Thank you very much indeed. Excellent presentation. I clearly have a lot of interest in PBMR because of technology that I was involved with from the beginning. And I think it just indicates how forward-thinking that project was. It's just a pity we didn't get the thing through to the end. And that's a debate for a long time. But with that, and I'm going to say that we've run horribly over time, I'm sure. It was fascinating. I failed to be a proper controller. I'm just going to, so far we've had only 2 questions raised, and so I'll look at those questions and see if I can, one I'll answer myself and one I'll pass on to Mark. The first question, someone asked what OECD is. And the OECD is the Organization of Economic Cooperation and Development. It's very much a first world group of about, I think, 20 countries, it could be 15, but it literally includes the major European countries, the USA, Canada, Japan, I think South Korea, and Australia. It's that kind of organization. And it has a series of organs, and the impact, and they organization called the International Energy Agency, not the International Atomic Energy Agency, so it gets confused. It's IEA, which was they set up in 1979, I think, after the oil crisis to try and track for their economies how the energy in the world was going. And that's where those studies I showed earlier come from. The other question is one, the next question is one from Ludwig. And it's a question aimed, I believe, at Mark, so I'll pass across to Mark for this one just to verbally answer it. Is there any development work into maritime industry, e.g. nuclear powered ships?
Yeah,
Mark?
Thanks. Can you hear me?
Yes.
Great. Okay, that is actually a great question. And the answer may be less, the short answer is for USNC at the moment, no. But I think it raises a topic about offsetting carbon emissions. And nuclear powered ships are in fact not as much of a pipe dream as you might think. I think there have been, the US built one cargo ship, Germany built a cargo ship, and the Russians have several commercial nuclear powered ships. So it's not at all a crazy idea. Right now, that's not one of our focus areas, though. Thank you.
Okay, I'm going to move quickly. The next question is from Kitalo. It's from your experience, what has been the environmental impact? I'm presuming you're talking about of nuclear on the society, and the answer is we can't really measure it. And I'll answer myself this one more. Essentially, the emission standard that a nuclear plant is given to emission to the public is normally below 1 microsievert per year. In the case of Coburg, below millisievert. In the case of Coburg, it's a quarter of that. The current emissions measured from nuclear stations is normally fractions, well, the order of a couple of % of the limit, and they're trying to drive it down further. So environmental impact from nuclear has been negligible. If you talk about accidents, it's very funny. The environmental impact of Chernobyl has been wonderful, because you've now got an area, the best game reserve in the middle of Northern Europe is around Chernobyl, where if you've been there, and I went there a few years ago, the animal life is amazing. Public health issues are very minor. But the environmental impact, sorry?
Oh, sorry, Dave, I thought you were finished. I just wanted to dovetail on that, if I may.
Yeah, go on. Mark, you?
There's a great case study that, Dave, you answered from the sort of the potential negative impacts, but I think it's important to observe the positive impacts. And a great case study is Ontario. I am not an expert on this, but I've heard people speak about it, and I found it fascinating that Ontario decarbonized effectively their electricity generating sector over the last 10 odd years by shifting from a blend which had nuclear, hydro, and fossil fuels, coal, and effectively eliminating the fossil fuels, the coal largely, and most of the gas. Now, what's really interesting about that, from the carbon emissions are hard to see, but the quality of life or the quality of air in Toronto is noticeably different, and people comment on it. So, using something like nuclear, which all of the waste generated is immediately captured and stored and disposed of responsibly, has a huge net positive environmental impact. So that I just wanted to add that because I think it's a great story.
Okay, I'm going to move off this one because I could go on for days on this discussion, but it's scary how confused everyone is. In fact, nuclear power's health effects, including Chernobyl and Fukushima and everything else, is internationally accepted to be significantly less death rate than solar panels on household roofs. The next one, and I'm going to be naughty, and I'll answer the first one without asking Riedewaan because he's an Eskom person and I was. How much does the 4,000 megawatt PBMR cost in USD? Just by context, the unit size was 165 megawatts electrical, if I'm rightly. It was 400 megawatts thermal. That was the official discussion. And the target value was realistically probably to get down in mass production down to about, I would say, between $2,000 and $3,000 a kilowatt, which is the current number of the classical large reactor is today, if you ask the domestic programs in Russia and China and India and South Korea. The other question being asked to go with that is how much does the MMR cost? So Mark, that's your call. How much does your plant cost? I want to buy one next week, please, and put it in my back garden. Yeah. How much does it cost?
So we imagine, just to be clear, selling these through PPA, because operating a nuclear plant is complex and probably in most of our client space not interesting. And we see that we'll sell power today at about the same rates that renewables were 10 years ago. So the very first plants coming off the production line will sell between 20 and 25 US cents a unit, a kilowatt hour. And that's you know, a nice metric because it enables you to easily compare to other technologies. The capital cost is quite high, and it does drive that. But what's really important about that is that the capital cost also includes 20 years fuel. There's very few other technologies which really have that.
Okay. Okay. The next. Oh, sorry, I missed one here. How is Eskom? This one I'll ask the Riedewaan. How is Eskom intending to ensure the socio-economic development within the nuclear power project framework?
Yeah, so it's a thanks. That's a good question. We've got a project infrastructure model that builds that specifically, and part thereof is the socio-economic development aspect. With the project that had started in 2016, there was a move to restart a nuclear commercial or nuclear program. One of the benefits, and we had engaged quite closely with the areas around the plant and the municipalities, the people around the plant, was to put together a socio-economic development framework to understand the benefits thereof, and it's a key part of the assessment that would go with any nuclear plant, to understand the benefits from a socio-economic perspective, and when assessing, if one were to assess an offering from any supplier out there, we would build that factor in to understand the benefits to things like localization, job creation, skills development, and infrastructure development around a power station, industrialization, that sort of thing. So it's a key aspect that we do look at with any new nuclear.
Okay. I'm going to take the last question because I'm aware that we're horribly over time in many ways. Question from Sammy. In terms of operation and maintenance of MMRs, I'd like to hear the response from Mark. I'm presuming that is, what is the operations and maintenance issues for the MMR? What sort of staff level are we talking about? What sort of operation involvement are we talking about? So Mark, over to you.
Yeah, thanks. I mean, that's a very pertinent question. The reason it's pertinent is that when you're operating reactors at this scale, even adding one extra operator on staff is potentially changing the tariff, changing what it costs to generate power. So we are very focused on making sure that we optimize this. You know, we do everything we can in terms of using established technologies and equipment with a track record. But we understand this is a piece of power generation equipment. It's not standalone. We will have operators tending it and controlling it. And really, our real aim is to use all of the characteristics of the reactor and the technology to reduce the load on operators and to be able to use less operators. And so that's really our focus there. The real numbers are in flux, and the first plant will demonstrate realistic numbers. But you know, we definitely know that we'll have probably multiple operators on site all the time to make sure that the plant is reliably delivering the power that the customers need. I hope that answered the question.
Thank you. I'm going to make one question. Stig has asked, are the copies of the presentations going to be shared? I'm presuming the answer is on the SAIEE website. Douglas, are you there to answer that question?
Yes, Dave, they will be placed on the website. All the presentations will be available. Thank you.
Okay, thank you, Pat. And with that, I think we're going to draw to the end of this webinar. Thank you for the presenters, and thank you very much for the questions from the attendees. So thank you for attending the SAIEE technical talk today. Please visit the SAIEE website, which is at www.saiee.org.za for upcoming webinars. And with that, I am going to close the webinar. Thank you all. Enjoy the rest of your day.